Hey everyone, and welcome back to Complicated Stuff. I'm Thomas and Ron. Wow, I can't believe we're already at episode 15.
It really is amazing how quickly time flies,
Yeah.
Especially when you're exploring all of these mind-bending topics.
Yeah, you said it. As always, I'm here with Jenna. She's our resident quantum expert, and she's the one that keeps me grounded. Especially when we venture a little too far into the theoretical. We're both part of the Girl Has It All team, and we're really all about helping you discover your own potential, even if that means understanding complicated stuff.
That's right. And today, we've got a really interesting mix for you. We're going to be talking about everything from these massive solar projects to maybe the need to tweak Einstein's theories a bit.
That's right.
And even the possibility of actually seeing naked singularities. So buckle up. It's going to be a wild ride.
Okay, so let's start with something that's a bit closer to home, literally. China is building this massive solar energy project. It's being called like the Great Solar Wall. And it's in the Kabuki Desert. We're talking 400 kilometers long, 5 kilometers wide, and a price tag of $48 billion.
It's mind-blowing, just the sheer scale of it. But what I find really fascinating is how this project is designed to really tackle multiple problems at the same time. It's not just about, generating clean energy. It's also about combating desertification and even creating jobs.
So tell me a bit more about that. How does a giant wall of solar panels, actually fight something like desertification?
Well, the panels actually act like this huge sunshade over the desert. And what that does is it prevents soil erosion, and it also protects the Yellow River. And plus, they're incorporating farming practices underneath the panels, so it's really a win-win for both energy and agriculture.
That's a really interesting approach. Makes you wonder if something similar could be done in other regions, that's dealing with desertification. Switching gears a little bit, let's talk about Einstein's theory of general relativity. I was reading that some research is suggesting that we may actually need to modify it. That's kind of a big deal, right?
It is a big deal. I mean, Einstein's theory has been incredibly successful in explaining gravity and how the universe works at large scales, but there are some things that it doesn't quite explain, like the accelerating expansion of the universe.
Right. I remember hearing about that. Didn't scientists come up with this concept of dark energy to try and explain that acceleration?
Exactly. But a dark energy is still a big mystery.
Yeah.
We don't know what it is. And some scientists believe that it could be a sign that our understanding of gravity needs some tweaking, especially at vast distances.
Okay, so how are they trying to tweak Einstein's theory?
Well, they're taking a really close look at data from the Dark Energy Survey, which is mapping out the distribution of galaxies. And they're specifically studying how gravity bends light from those distant galaxies. It's a phenomenon called gravitational lensing. And what they're finding is that these gravitational wells, where gravity warps space-time, aren't as deep as Einstein's theory predicts.
So the light isn't bending as much as it should be.
Right. And this is particularly true for the period when the universe's expansion started accelerating. It suggests that gravity might behave a little differently at these vast cosmological scales.
So are they saying that Einstein was wrong?
Not necessarily. I mean, his theory works incredibly well in most situations, but it might just need some slight modifications to account for what we're seeing at these huge distances.
What kind of modifications?
Well, some scientists are introducing these new parameters into Einstein's equations. Things like mu and eta. You can kind of think of them as knobs that you can adjust to fine-tune the theory. Mu describes how gravity might change at vast distances, and eta deals with how time and space are distorted on those scales.
So by adjusting these knobs, they can try to make the theory match the observation.
Exactly. It's like trying to solve a cosmic puzzle. You're trying to figure out how all the pieces fit together. And this research could lead to some really revolutionary ideas about the universe. It might even point to new forces or particles that we haven't even discovered yet.
Wow, that's pretty wild. I'm starting to see why you called this a wild ride.
Yeah.
But before we get too lost in the vastness of the cosmos, let's talk about something that's equally fascinating, but at the opposite end of the size spectrum, quantum gravity.
Ah, yes. The holy grail of physics, trying to unify the laws that govern the universe at its largest scales with the really weird world of quantum mechanics.
Yeah, it sounds like one of the biggest challenges in science. Where do we even begin with something like that?
It is a massive challenge, but there are some really exciting avenues of research. One of them involves something called primordial naked singularities, or PNs for short.
PNs, what are those?
Okay, so imagine a black hole, a region of space-time, where gravity is so strong that nothing Not even light can escape.
Okay, got it. Those super dense things that form from collapsing stars.
Right, now imagine a black hole, but without its event horizon. You know, that boundary, beyond which nothing can return. That's essentially what a naked singularity is. It's like this incredibly dense core that's exposed to the universe.
So you're saying that there might be these points of infinite density just floating around in space, potentially observable.
It does sound pretty wild, but that's what scientists are theorizing. They believe that these PNs might have formed in the very early universe, before black holes even had a chance to develop their event horizons.
So they're like remnants from the Big Bang.
Sure.
Fossils of the universe's earliest moments.
Exactly. And because they lack those event horizons, we could potentially observe them directly, giving us this glimpse into the extreme conditions where gravity and quantum mechanics collide.
Wait, so we could actually see the quantum nature of gravity at work.
That's the hope. It would be like having a cosmic microscope that allows us to peer into the very fabric of reality.
This is blowing my mind. But there's one more thing I remember reading about PNAS. They might also be connected to dark matter.
You're right. PNAS could potentially make up a significant portion of dark matter, that mysterious substance. That seems to make up about 85% of the matter in the universe.
Hold on. So these mind-bending objects from the early universe, these naked singularities, could be the very stuff that's been eluding our detection for decades.
A possibility. We know dark matter exists because of its gravitational influence on galaxies and galaxy clusters, but we've never been able to directly observe it. And PNAS might be so dense that they don't interact with light in the same way that normal matter does. They could literally pass right through it, making them invisible to our telescopes.
Wow. So they could be all around us, exerting their gravitational pull, but remaining completely hidden from our view.
It really adds a whole new layer of mystery to the cosmos, doesn't it?
It definitely does. But for now, let's shift our focus from the vastness of the universe to something a bit more down to earth, shall we? Tell me about these metal organic frameworks, or MOFs, that I keep hearing about.
MOFs are these incredibly versatile materials, and they have these tiny pores, which makes them excellent at capturing and storing specific molecules.
So they're like microscopic sponges.
That's a great way to put it. Imagine a honeycomb with all those tiny compartments, but at a molecular scale.
Okay, I can picture that. But what makes them so special?
Well, their potential applications are incredibly diverse. For example, they're being investigated for carbon capture, pulling CO2 directly from the atmosphere.
That's huge. We definitely need solutions like that to fight climate change.
Absolutely. And they're also being studied for drug delivery, creating these targeted systems that only release medication at specific locations in the body.
That's amazing. So instead of flooding the entire body with a drug, you could deliver it directly to the affected cells.
Exactly. This could really increase the effectiveness of treatments while minimizing all those nasty side effects.
It's incredible how something so tiny can have such a big impact. But I'm curious, what's the biggest challenge in working with these MOFs?
Well, one of the biggest challenges is actually controlling the movement of molecules within those tiny pores. It's like, imagine trying to direct traffic through a maze, but at the atomic level.
Okay, that sounds incredibly difficult. How are scientists even approaching that?
They're getting incredibly creative. Recent research has actually shown that it's possible to manipulate the chemical interactions within MOFs to control the diffusion of specific molecules.
So they're basically creating molecular traffic control.
That's a great analogy. By fine-tuning that chemical environment inside the MOFs, they can speed up or slow down the movement of certain molecules, essentially separating them from a mixture.
That's mind-blowing. What are the implications of something like that?
Well, possibilities are vast. This discovery could revolutionize industries that rely on chemical separations. Everything from petrochemicals to pharmaceuticals. Imagine being able to purify chemicals more efficiently, using less energy, and generating less waste.
That would be a huge win for sustainability.
Absolutely. It's a perfect example of how fundamental research, even at the microscopic level, can lead to practical solutions with real-world impact.
It's amazing how these different areas of research are all connected, from the vastness of space to the tiniest molecules. But it's getting late, and I think we need to take a break. When we come back, I want to dive deeper into the potential applications of these technologies and explore what they mean for the future.
That sounds great. And I'm sure our listeners have a lot of questions and thoughts of their own, so don't forget to connect with us on social media. We always love hearing from you. Stay with us. There's so much more to explore. Welcome back to Complicated Stuff.
It's great to be back with you all, diving deeper into these fascinating topics that really are pushing the boundaries of human knowledge. And before the break, we were just wrapping up talking about the potential of MOFs, and it really feels like we're on the verge of like a material science revolution.
I agree, the possibilities with MOFs seem almost limitless, and one area where they could have a truly massive impact is in chemical separations.
Yeah, you mentioned that before the break, but I'm kind of having trouble picturing it. How can these tiny pores revolutionize an entire industry?
Okay, so think about it this way. Many industrial processes, especially in the chemical industry, rely on separating and purifying different chemicals, right? And oftentimes these processes are incredibly energy intensive and not very environmentally friendly.
So like those giant distillation towers you see at chemical plants, those always seem to be billowing smoke.
Exactly, but with MOFs, you could potentially create much more efficient and sustainable separation methods. Imagine designing pores that are precisely tailored to trap only the molecules you want while letting everything else pass through.
Okay, so it's like having a filter at the molecular level. That's pretty neat. What would that look like in a real-world application?
Okay, let's say you're trying to capture carbon dioxide from industrial emissions.
Okay.
You could design a MOF with pores that specifically trap CO2 molecules, effectively filtering them out of the exhaust stream.
It would be huge for reducing greenhouse gas emissions.
It would, or imagine using MOFs to purify water. You could create a membrane with pores that allow water molecules through, but block contaminants, providing clean drinking water in a much more efficient and sustainable way.
It seems like this technology could have applications in so many different fields.
It really does, and that's what's so exciting about MOFs.
Yeah.
I mean, we're really just scratching the surface of their potential.
Well, I, for one, am excited to see where this research goes, but for now, let's shift gears back to the cosmic scale and revisit those mind-boggling, primordial, naked singularities we left off, talking about how they might be connected to dark matter. But how would we even detect something that's essentially invisible?
That's a great question, and it leads us to one of the most exciting new frontiers in astronomy, gravitational wave astronomy.
Ah, yes, gravitational waves. Those ripples in space-time caused by the acceleration of massive objects. Didn't scientists recently win a Nobel Prize for detecting them?
They did, and it's opened up this whole new way of observing the universe, you see. While we can't directly see PNS with traditional telescopes, they would still exert a powerful gravitational influence.
So even if they're invisible to light, they would create these ripples in space-time.
Exactly, and we can detect those ripples using incredibly sensitive instruments like LIGO and Virgo.
I remember hearing about those projects, those giant L-shaped detectors, right?
That's right. They're designed to pick up the incredibly tiny distortions in space-time caused by these gravitational waves. And if these PNS are as dense as theories predict, they would generate very distinct gravitational wave signatures.
So we might be able to hear these naked singularities before we can see them.
It's a fascinating possibility, and it highlights the power of what we call multi-messenger astronomy, which combines observations from different sources like light gravitational waves and even neutrinos to really paint a more complete picture of the universe.
It's like we're using all of our senses to explore the cosmos. Pretty amazing, right?
It is, and this multifaceted approach is proving to be incredibly valuable in the search for these really elusive phenomena like PNS.
So by combining traditional astronomy with this gravitational wave astronomy, we might finally be able to unlock the secrets of these mysterious objects. But I'm curious, beyond just satisfying our scientific curiosity, what are the implications of finding these PNS? What would it mean for our understanding of the universe?
Well, one of the most significant implications is for our understanding of quantum gravity, as we discussed earlier. Black holes, with their event horizons, have always been a bit of a black box for quantum gravity theories.
Because we can't see what's happening inside the event horizon.
Exactly. The event horizon acts as this barrier, hiding those quantum gravitational effects from our view. But with naked singularities, there is no such barrier. We could potentially observe the quantum nature of gravity directly.
Okay, I'm starting to see why this is such a big deal, but it's hard to wrap my head around the idea of quantum gravity. What does it even mean to say that gravity is quantized?
It's a really complex topic, but essentially it means that gravity, like light and matter, exists in these discrete packets, or quantum gravity. So instead of being this smooth, continuous force, gravity would be made up of these tiny, indivisible units.
So instead of like a flowing river, it would be more like a stream of individual droplets.
That's a good analogy, and this quantization of gravity would have really profound implications for our understanding of the universe, especially at the very smallest scales, like the Planck scale.
The Planck scale, what's that?
The Planck scale is the smallest possible unit of measurement in physics where even space and time themselves become quantized. It's the realm where quantum mechanics and gravity truly collide.
Wow, we're really getting into the deep end here. It's amazing to think that these naked singularities, these remnants from the Big Bang, could hold the key to unlocking the secrets of quantum gravity.
It is, and it shows how the search for these seemingly exotic objects isn't just an intellectual curiosity. It's a quest that could fundamentally change our understanding of the universe and the fundamental laws that govern it.
It's a good reminder that the most profound discoveries often come from exploring the most extreme and seemingly bizarre aspects of the universe. But for now, let's bring our focus back down to Earth for a moment. We've been talking a lot about the potential benefits of these technologies like MOS for carbon capture and clean water. But what about the potential downsides? Are there any ethical considerations we need to be thinking about?
That's a crucial point. As with any powerful technology, there's always the potential for misuse or unintended consequences. We need to think very carefully about who has access to these technologies and how they are used.
So it's not enough to simply develop the technology we need to make sure it's used responsibly and ethically, but who's responsible for ensuring that?
That's a complex issue, and there's no easy answer. It really requires a collaboration between scientists, policymakers, ethicists, and the public to ensure that these technologies are used for good and don't exacerbate existing inequalities.
Yeah, this is a really important conversation to have, and it makes me think about one of the core values of Girl Has It All, empowering individuals through knowledge and self-discovery. We need to be informed and engaged citizens if we want to shape the future of these technologies.
I couldn't agree more. It's all about fostering critical thinking, encouraging curiosity, and inspiring a sense of wonder about the universe and our place within it.
Well said. And on that note, we're going to wrap up this part of our discussion. Stay tuned, though. When we come back, we'll dive into some listener questions and explore what all of this means for the future of science and humanity. Don't go anywhere. Welcome back to Complicated Stuff. We've covered so much ground today. From China's ambitious solar project to the mind-bending world of quantum gravity and those intriguing metal-organic frameworks.
It's been quite a journey. And as promised, we wanted to open up the conversation a bit and hear what you, our listeners, think about all of this.
That's right. We've got some great questions from our social media followers. So let's dive right in. The first one is about those primordial naked singularities. A listener named Sarah asks, if these PNS are so dense, wouldn't they have a huge gravitational pull? Could they be dangerous to Earth?
That's a really interesting question, Sarah. It's true that PNS would have a strong gravitational pull, but remember, we're talking about objects that are incredibly small, likely on the scale of subatomic particles.
So while their density is immense, their overall mass might not be that significant.
Exactly. Think of it this way. A single proton in an atom's nucleus is incredibly dense, but it doesn't exert enough gravity to pull in everything around it.
Okay, that makes sense. So even if we're surrounded by these PNS, their gravitational influence on Earth would be pretty negligible.
That's right. They wouldn't pose any direct threat to our planet.
Great. That's reassuring to know. The next question is from Mark, who asks, you mentioned that MOFs could be used for carbon capture. How realistic is that? Could they really make a dent in climate change?
It's a great question, Mark, and a very important one. The potential of MOFs for carbon capture is huge, but there are still some challenges to overcome.
What kind of challenges are we talking about?
Well, one challenge is scalability. Right now, we can create MOFs in a lab setting, but producing them on the massive scale needed for industrial carbon capture is a different story.
So it's a question of engineering and manufacturing.
Exactly. We need to find ways to produce MOFs efficiently and cost-effectively if we want to use them on a global scale.
But the potential is there.
Absolutely. MOFs have a much higher capacity for CO2 capture than other materials, and they can be designed to be incredibly selective, which is important when you're trying to remove CO2 from a complex mixture of gases.
Okay, so it's a technology worth investing in and researching further.
Definitely. If we can overcome those engineering challenges, MOFs could be a game changer in the fight against climate change.
Well, let's hope those challenges are overcome sooner rather than later. We need all the help we can get on that front. The last question for today is from Maria, who asks, What are your thoughts on the ethics of manipulating matter at the atomic level? Do you think there are any risks we need to be aware of?
That's a very thoughtful question, Maria, and it gets to the heart of the responsibility that comes with scientific advancements. Anytime we gain new powers, we need to think carefully about the potential consequences, both intended and unintended.
So it's not just about what we can do, but what we should do.
Exactly. With technologies like MOFs and other nanomaterials, we're entering a new era of material science, where we can manipulate matter with incredible precision. But with that power comes our responsibility to use it wisely.
What are some specific risks we should be considering?
One concern is the potential environmental impact of these materials. What happens when they enter the environment? Do they break down harmlessly? Or could they accumulate and cause problems?
So we need to think about the full life cycle of these materials, from production to disposal.
Absolutely. And we also need to consider the potential social and economic impacts. Who will benefit from these technologies? Will they be accessible to everyone? Or only to those with the resources to afford them?
These are all really important questions, and I think they highlight the need for open and transparent dialogue about these technologies. We need to engage with the public, policymakers, and ethicists to ensure that these advancements are used for good and don't exacerbate existing inequalities.
I completely agree. It's not just about pushing the boundaries of science. It's about using that knowledge to create a better future for everyone.
Well said. And that brings us to the end of our show for today. It's been a truly mind-expanding journey, and we hope you've enjoyed it as much as we have. We've covered a lot of ground, but there's so much more to explore out there, and we're just getting started. We'll be back next week with a whole new set of complicated stuff to unravel.
In the meantime, keep those questions coming, connect with us on social media, and let's keep the conversation going. We're all in this together, exploring the universe and our place within it.
This is Complicated Stuff signing off.